Okay, this is the 7th grade universal law of gravity test. So we are analyzing a mysterious planet. Okay, number one, you suspect that there is an undiscovered ninth planet 500 million kilometers away. Now, first of all, we have to convert this to meters. So 500 million is 5 times 10 to the 8th, and this is in kilometers. To convert from kilometers to meters, that's 1,000 meters to 1 kilometer, which is 5 times 10 to the 11th. Okay. Past the planetoid Pluto, and Pluto is approximately 6 billion. 6 billion is 6 times 10 to the 9th, and that is kilometers, so times 10 to the 12th. That's meters. What would you predict the force of gravity between the sun and the mysterious planet? All right, so we're going to need our force of gravity equation. Our large G there is our gravitational constant. That's 6.67 times 10 to the negative 11. And we're going to go ahead and put that into our equation. So our gravitational constant times the mass of the planet 1, which is 6.4 times 10 to the 23rd, times 2 times 10 to the 30th, that's the mass of the sun, divided by the distance between them. Now, the distance in this question is 6 billion kilometers plus 500 million kilometers. We convert that to meters, so that is going to be 6.5 times 10 to the 12th meters, and that is squared. We put that into our calculator, we get 2.0 times 10 to the 18th, which is number 1. You suspect the planet exists because its effect of its gravity has on nearby asteroids. You know the mass of one particular asteroid is 75,000 kilograms. This is actually a bit of a distractor, but you don't know that yet. You observe the asteroid for 1 year. What is year in standard scientific notation? So 1 year is equal to 365 days. Now, if you want to do 365.25, you can. It's not going to make a huge bit of difference for this particular problem. Times 24 hours in 1 day. Days cancel out. Times 3,600 seconds in 1 hour. Hours cancel out. And I am left with 3.156 times 10 to the 7th. That's seconds. That's how many seconds there are in a year. All right. Now let's continue reading. So how much displacement? Okay, I'm looking for displacement from an initial relative velocity of 0. Now, this relative initial velocity has to do with the fact that planets are always in motion. So it's relative to what? It's kind of relative to each other. Right? So we know our initial velocity is going to be 0, and we're going to see how much this asteroid is attracted or pulled off course by this planet. And they have a distance of 50 million kilometers. Again, we have to convert that from kilometers to meters. 50 million is going to be 5 times 10 to the 7th kilometers, which converts to 5 times 10 to the 10th meters. We are ready to put them into our equation. So which equation are we going to do? Well, our displacement equation up here has an initial velocity times time, and our initial velocity we said was 0, and we do have a time of this many seconds, times 0.5 times the acceleration, which we don't have yet, times time squared, but we can find our acceleration using our force equations. So let's go ahead and put that in. Our displacement is going to equal 1/2 acceleration times time squared. Don't forget the squared. So what is our acceleration? Well, we need to do the gravitational equation, which is the force of gravity is equal to our gravitational constant times the mass of the planet. I'm just going to do plus m1 times the mass of the asteroid all over the distance between them. That's r squared equals if you remember, force is equal to mass times acceleration. So this is the force. The mass of the asteroid times the mass of the acceleration, all right? Mass of the asteroid cancels out. Remember that all objects in gravity are going to accelerate at the same rate depending on what object they are. So the masses, they will always cancel out. And that leaves us with acceleration. Let's go ahead and put our numbers into our calculator. This is going to be 6.67 times 10 to the negative 11 times the mass of the planet, which is 6.4 times 10 to the 23rd. And divide that by the distance between them, which we said was 5 times 10 to the 10th. We could find the acceleration of the planet towards the asteroid too, but this number would be just astronomically small. But that would just be fun. So let's go ahead and put this into our calculator, and we will get 1.71 times 10 to the negative 8. Don't forget to square that. All right, so that's the acceleration. It's not much acceleration, and you'll find that that's true of gravity generally. We're dealing with like huge distances here, and the force of gravity is just very, very small. And as you remember, whenever you square something, you get it is a squared distance. So gravity decays at a square of the distance. It decays very, very quickly. However, we're still dealing with a long period of time, so let's go ahead and put that into our equation. That is going to be 0.5 times 10, not times 10, times 1.7 times 10 to the negative 8 times 3.156 times 10 to the negative 7, but I'm running out of space. Just put that into our calculator real quick. And I'm going to get 8,503,736 and some change. So this is going to be 8.4 times 10 to the 6th. So it looks like it rounded a little bit when I made this question. Okay. Even though you weigh 500 newtons on Earth, what do you expect you'll weigh on the new planet? All right, so 500 newtons on Earth. This is a weight. We calculate weight by force is equal to the mass times the acceleration, and this is due to gravity on Earth, which for our purposes, we usually round to 10. That's what we've done here. So the force of gravity is going to be 500 equals the mass times 10. So the mass is going to equal 50 kilograms. Right. Remember that your weight is just the force of gravity. If you wanted to, you could have calculated this using our gravitational equation, but this works just fine. Okay, so the mass is this. Now we need to figure out what the acceleration due to gravity is going to be on the new planet. All right, so let's go ahead and sort that out. It's going to be a gravitational constant times the mass of the planet, which is going to be 6.4 times 10 to the 23rd, times the mass of the person, which is 50, but we can just put that in there, and that is going to be divided by the radius of the mysterious planet. So remember that it is this distance here, not the diameter, which is up here. So half this diameter is going to be 3.4 times 10 to the 6th. 3.4 times 10 to the 6th. And all of that is squared, and that is going to give us the force of gravity, or the weight, on this new planet. So let's go ahead and put that in. That is going to give us a value of 184 and some change. 0.6, I think. And when we do that, this is going to be the weight. So we can see that it is significantly less than on Earth. So I'm just going to go ahead and do that. Okay, let's go on to the next problem. Your spaceship and all your cargo has a mass of 60,000 kilograms. How much work do the engines have to do to get your spaceship into orbit, which is not kilometers, which is going to be 1.3 times 10 to the, if this is 4, then we add 3 is 7 meters. from the surface of the planet. Assume the force of gravity from the center of the planet to the surface doesn't change significantly from the surface to orbit. It actually does a little bit. If we were doing this in real life, we would probably have to account for that, but I don't feel like doing the calculus today. So we are going to have to figure out what the force of gravity is on this particular planet. So let's go ahead and figure that out. So the force of gravity, which we can just go ahead and put this into here, because we are going to want to do work is equal to force times displacement. And the displacement is going to be here. So we need to find the force of gravity on this 60,000, which is going to be the gravitational constant times 6.4 times 10 to the 23rd times 6.0 times 10 to the 4th, all over 3.4. Remember, this is the radius to the surface of the planet, times 10 to the 6th, and that's going to be squared. We put that into our calculator, and we are going to get 2.21 times 10 to the 5th. Okay, so and that will be in newtons. That's our force. Our displacement is going to be this number, so this is going to be 2.121 times 10 to the 5th times 1.3 times 10 to the 7th. Put it into our calculator, and we are going to get 2.88 times 10 to the 12th. And we're just going to round up to 2.9. Over there. All right. You would like to test the acceleration due to gravity on this planet. So you drop an object from 275 centimeters. No, 2.75 meters. How long did it fall? Okay, free fall equation, we've done this lots of times. So this is displacement is equal to 1/2 times the acceleration, which we have figured out previously, times the time, which we're trying to figure out. Okay. So our displacement is 2.75. Our acceleration due to gravity is going to equal the 3 point something that we discovered before. Let me go ahead and find that real super quick. 3.69 times our time squared. If you're not sure how I got this 3.69, it is just